Today at Devolution, they say that some things just aren't made like they used to be. And in this video, we're going to see if that applies to the cheap 532 nanometer laser pointers. So, I'm going to take apart a couple of them and we're going to see exactly what's changed for the worse. Starting with the laser pointer that's the newest from 2022-23. This one right here, which cost me $3. Comes directly from the manufacturer in China. From 2015, we have this laser, which was bought at an estate sale and resold on eBay. And the oldest laser pointer we're going to take apart is from the mid-90s. It was bought at a tool trade show. So, what could possibly have changed in the last couple of years? Well, let's see what they weigh. So, I'm going to weigh the newest laser pointer first. About 20 grams. The one from 2015. So this one already weighs 1/3. One full half heavier than this. So, yeah, all right. And this one from 1995. 45 grams. So, seems like with these iterations, they drop about half the weight of the original one. So, this one weighs 2/3 the weight of this one, and this one weighs 2/3 the weight of this one. Very interesting. All right, well, yeah, there's a big difference. 20 grams versus 45 grams. And it's going to be interesting to see exactly what's changed on the inside of these, isn't it? All right, well, let's start with the lightest and newest one first and go back in time with our fancy time machine. And by time machine, I mean assorted tools in the workshop. All right, so I'm going to take these apart all in a very similar way. And that is popping this part in the back, little foam piece out. I'm going to pull the front end cap right here off, and to prevent any kind of scuffing or scraping or marring on that surface, I'm going to throw some electrical tape around there beforehand, and that way I can grab it with the tool and work it off. So, just like this. Good enough. Scissors. Do we need scissors? Nah, we'll forget about scissors for the time being. We have work to do. Alright, and extracting. Worked quite well. Doesn't seem like there's any seeable damage on there, so that looks like it worked really well. Perfect. Cool. Well, that leaves us with this. So to get the actual module out of these, I like to go at it from two ways. First, I'll go at from the battery negative contact point. I have this little piece that I put in the back of the tube, and it has this cutout right here. So when I slide it forward like this, there's room for the button to drop in. And there's a little black piece on the inside there that supports the PCB. And this is gonna rest against that, and it's gonna push it through this way up to a certain point, just like this, and forward. All right. We're gonna need the vise for that. Yeah, this may be the wrong vise to use. Yeah, might be. We're gonna see. I gotta open this up all the way. Where's my other vise? Is it around here? Bad planning on my part. Right, I'm gonna need to grab the other vise. One moment. All right. Tool exchange time. Oh, just barely. Look at that. What do you know? All right. See if I can sneak something in the front to protect the front from getting goofed up. That's gonna cut right through there. That's okay. This is a cheap laser. We can make some cosmetic sacrifices. All right, here we go. And I'm waiting for the button to kind of drop in. Make sure that it's not getting stuck on the spring. Sometimes it does that. Oh, that's good and jammed now. Great. Tools. Nope, we're good. Let's keep going. Oh, is it buckling here on the top? It might be buckling there a little bit on the top. Oh, no, it's going. Good, good. It's either being taken apart or being destroyed on the inside. Either way, I'm actually okay with what's going on here. Oh, well, can't get that out right now, so let's go ahead and try to grab it from the front. So the second way that I remove these modules is I take the collimating lens off. So grab that. I can't grab that with that tool. Let's try this. That's working. Okay. I take this piece, I thread it on in place where the collimating lens was. Just like that. We'll put it in the other vise. And as I said over and over again, this is the part that nobody likes, because taking these apart can be a nightmare. Looks like on this one we're just going to have to use the good old soup can method. Pretend like this has a twist top. Boy, that broke off too. So far, 2022 ain't looking very good. Alright, well, we're not going to take a look at this directly right now, but needless to say, it has earned itself a very poor ease of disassembly score. Move that off to the side. We'll collect these bits and scraps and analyze them later. Let's see if the 2010s fares better than the 2020s. Go ahead and see if I can pull this laser apart. Actually, you know what? Pull the collimating lenses out first. Put that into our 2010s pile. Okay. Looks about the same. Go ahead, put it in the vise and pull the module out. Maybe with a little less carnage. Oh, this one's gonna earn itself a high repairability score too, isn't it? All right. It can be taken apart. That's some points in its favor. That stayed intact. Good. And let's see if anything else broke during this. process. Hey, the lens didn't fall off either. What do you know? Okay, so 2015 already looking better. Alright, let's move on into the 90s. Let's take apart this laser now. Hopefully this comes apart all nice and neatly, considering this is the old, expensive, vintage one. Well, that's a good sign. Now how am I going to get it out? I got it. I know exactly what I'm going to do. Duh. Super simple. Where did I put that? That's it. Yeah, I know the threads don't work. That's fine. That's perfectly fine. Perfect. All right. And that's that one. Now that we have extracted our modules, I think what I might do is carefully glue the expanding lenses back on, and it will come to comparing the differences between the actual laser modules themselves. Before we get into comparing the laser modules themselves, let's take a look at the components of the laser pointer housings and see how those differ. So starting with the one from 2022, I'm going to start with the back battery compartment section. So there's 4 main parts: the tail end right here, the pocket clip, the tube, and then the threaded insert here on this side of the battery compartment. So let's start with the tube here, or the threaded section. See what that is. Seems to be metal. Oh, yep. Looks to be a metallized brass, electroplated brass. The inside indicates that the tube is aluminum. Pocket clip is metal, probably regular old plated steel. It's magnetic. And then that leaves us with the back here. Is that metal or plastic? Go ahead, give it a tap. Sounds plastic to me. See if the razor goes in it. Oh yeah, very easy. So that's definitely plastic. Okay. Put that off to the side. We have a couple of pieces here of the front section where the module was. Let's go ahead and actually grab that all, and we'll see what the weight is. That's really the only way of directly comparing this with the others at this point. So total weight is 3.6 grams. We'll keep that in mind. The other thing we can do actually is measure the thickness of the aluminum. 0. Okay. Give that a good squeeze. 3.5. Sorry, 0.35. So about 1/3 of a millimeter on that. Okay. And the two other pieces to really kind of compare. Got the front dust cap right here. That feels plastic to me. Yep, plastic. And the button. The button just fell, but I assure you that that button was also plastic. It's a metallized plastic. Alright, let's take a look at the one from 2015. Starting with the battery compartment again. So, it looks to be aluminum. The threaded section is once again metal that has been plated. Focus. Or not, that's cool too. Let's take a look at the difference in quality in those real quick. See if I can zoom in, get a better view. Okay. Yeah, so it looks like the wall thickness is about the same. Okay. All these pocket clips right here, they're pretty much made of the same stuff. So I expect that to be magnetic. Yep. Leaving us with the back end here. So is that metal or plastic? Sounds metal. Go ahead, give it a little indent with the razor. And no mark is made. So the difference between these two right here is mostly that the back end has been changed from a metal to a metallized plastic. So there's some cost savings there. Alright. Let's see what the thickness is on this. So, other side. So about the same. See what the front is. This feels plastic. That is most definitely plastic. And this button here, also plastic. Right. So not much of a difference overall between those two. We'll take a look at the one from 1995. Not 2000 anything. It's a much heavier back end. This is definitely metal. Yep. Let's see. This right here, the tube. That's, let's see. What is that? Oh, okay. So this has a little battery insulator in it. Let's see if I can pop that insulator tube out. I might not be able to. I'm going to go ahead and give it a try. That's nice. A little bit of extra protection at their cost. Nope. Looks like that was put in before this was put in. So, yeah, let's see. Given that the other side is brass, this is also probably brass as well. Actually, can we just pry some of that tube off the wall here? I need a little pick. Little pick. You would have glue on you. That's terrible. That'll work. Boy, this is harder than it looks. Okay, yeah. That is definitely brass in there. So, another main difference between these, it looks like, is that they stopped using brass and went to using aluminum. This right here is brass too, not that, but the whole housing itself, and it's not aluminum. So there's going to be a weight difference on there because of the copper. 8.8 grams versus, yeah, so almost twice the weight on just this piece alone. Let's see. Yeah, metal on both sides. So this is going to be a fair bit heavier too because it's brass. 18 versus, yeah, so the housing itself is almost double the weight. Take a look at the front dust cover. That looks and feels like it's metal. That is definitely metal. And the button. That looks metal as well. Yep. In fact, that button's about a gram itself versus the other buttons, which is nothing. Well, almost nothing. So yeah, a big difference in the quality of just the housings. Oh, hey, it strikes me. So we got a kind of rubberized coating on these. This one's pretty well intact, but the eBay listing for this one said that the rubberized coating was failing. So let's go ahead and see if we can rub some of that off. Get some isopropyl. You know, I do that because I'm really wondering at this point now if the old one from 1995-ish had a rubberized coating on it to begin with. It might have. So if we take a look inside this area, is that a remnant of coating? It might be. It just might be. Ooh, under the pocket clip. Go ahead and pop that off. See if there's any evidence for that. Yeah, it looks like there was a coating there at one point in time. See it right here. Interesting. So this didn't actually start off being glossy. This was at one point also a rubberized coating on there as well. Interesting, interesting. Let's go compare some modules. So far in the video, I've been starting with the present day and working my way back to show you the differences. But now that I'm comparing the actual laser modules themselves, I think I want to start with the late 1990s and work my way forward, so that way you can see where they continue to cut some corners. Let's take a look at the oldest module that I have. So this is the one from the late 1990s. Let's start with the driver on the laser itself. I'll pop this piece of plastic off. Alright, so this is a true constant current driver. Let's take a look at what we have. We have this transistor here, which is probably an NPN transistor. This 1 ohm current shunt resistor. Looks like we have a decoupling capacitor here. Another capacitor here, so 2 capacitors. This might be a little inductor or a resistor. We have 2 more resistors here. LM358 operational amplifier. There's actually 2 op amps in there, but it only uses the one. And this right here, which is probably similar to a TL431, some sort of diode or adjustable, programmable precision current shunt. Another resistor right here, probably to set the voltage that's across this shunt, and a potentiometer here. So, yeah, it's a decent constant current driver. Nothing wrong with that. Take a look at the module itself, where it holds the laser diode, the host. We can see that there's a threaded ring that holds the laser diode in position, so you can actually remove the laser diode by taking this ring out. That's nice. It's serviceable. That's brass. This section right here is brass, and surprisingly enough, it's actually copper, it looks like. My first time seeing copper on a cheap green laser pointer. Of course, when these were made, they weren't exactly cheap, but they were definitely green. Where's the little scrapey tool? I've lost my scrapey tool. That'll work for a scrapey tool. Yeah, that's copper. Okay, so one of the changes they made from the late 1990s to the early 2000s was that they stopped using copper and they moved to brass. You can see this in my older YouTube videos. They kept the same plastic carrier and collimating lens. That's all plastic. Another big change is with the ones from the late 1990s is they do have this ring that holds the laser diode in place. This retaining ring that you can change the diode in, extract the diode. In the ones that I had in the early 2000s, they were just press fit in, so you couldn't really remove the laser diode. Go ahead and take off the collimating lens. And you'll see this with almost all of them. So there's a plastic expanding lens that sits right here. A little brass host that holds the MCA, which is the two crystals, the ND-YV04 and the KTP. Let's see what else we can see. I'm going to see if I take the copper off the brass. Tools. Okay. Put that off to the side. Alright, so on the inside you can kind of see it. We have an open can laser diode. And the actual MCA, monolithic crystalline assembly, which is right here, is pressed right against the output of the laser diode. So there's no kind of condensing lenses on the inside. So, yeah. So that's how they used to look. Let's take a look at the one from the mid-2010s. Okay, so we still have a good driver board, it looks like. So there's the NPN transistor, 1 ohm current shunt resistor on the other side, LM358. Yep. We got the same resistors here. These resistors are actually for the current adjusting. So that's one thing they changed, is instead of using a potentiometer, which they carried on up until about the early 2010s, so 2005-ish, they had a potentiometer, and after that they changed to using fixed resistors. I think this is a lot to do with pop modding laser pointers, and they didn't want people to do that anymore, so they stopped using a potentiometer, so that way you couldn't turn up the laser. Still got an adjustable precision current shunt right here. This one is probably a TL431. Yep, okay. Couple other resistors. We still have 2 capacitors, full capacitor here. Okay, so they removed what capacitor? Looks like they might have removed an inductor. So 2 parts are gone. And they substituted the potentiometer for these fixed value resistors here. But it's still a constant current driver. Alright, let's take this off. Should expect to see the same thing, which we do. So we still have brass in here, and brass for the monolithic crystalline assembly mount, plastic expanding lens. The change from the mid 2010s to the late 2020s, early 2020s, somewhere. Okay, from 2005 to 2015, they changed this piece from being brass to being aluminum. They also put these fins on here, so that way when they press it in, kind of grips a little bit better, perhaps. But this also cuts down on the amount of heat that'll get out of this piece and into the hand to cool the laser down. So it's not as efficient for cooling. The copper is definitely better, and you have full, oh that's easy, and you have full contact with the copper, where you don't have the full contact because of those ridges. Let's see what's underneath the diode, or sorry, the monolithic crystalline assembly. Looks like there might be 2 lenses. Yep, I don't see the diode, so probably 2 lenses for condensing the laser beam onto the surface of the monolithic crystalline assembly. Got brass here. Let's see what's underneath this. Okay, so that's pressed in. There's no retaining ring. You really can't service this laser as far as replacing the laser diode. To try to get that diode out, you'd have to actually smash the 2 lenses that are in this in order to push that out. So not very serviceable. Though we already have a couple of reductions. So one capacitor has been removed, potentiometer has been changed. Looks like we lost an inductor. There's no retaining ring, and where it used to be copper brass here on the outside, it's now aluminum with this weird splining on it. So that's where some of the cost savings have come in from 1995 to 2015. Let's take a look at the modern state of laser pointers. You notice there's a big difference now. Let's take a look at the boards themselves. Alright, so where was I before I got so rudely interrupted by the lack of infinite storage space? Yes, comparing these two. So I got the module from the late 1990s, and I got the one from the early 2000s, and we can already see some differences. In fact, a lot of differences. So on the actual driver itself, we can see that there's the NPN transistor, capacitor, and the current shunt resistor. On here, we have absolutely none of that. So right there, lots of parts that have been removed. Let's take a look at the other side. And there's more parts that have been removed. So we no longer have the LM358 operational amplifier, or a current shunt, precision current shunt that can be adjusted for a voltage reference. So no voltage reference, no comparator, no NPN transistor, no nothing. So not a proper constant current driver here. They really are just banking on the battery voltage not being excessively high, so about 3 volts, and that drops the voltage down to the 1.8 of which this almost laser diode uses. That's another difference we have. So a lot of the laser diodes are 5.6 millimeter or 3.8. This one is neither. This one is some sort of weird flat package, as in plastic. So yeah, little plastic flat pack, and it looks to be an aluminum kind of wedge or spacer that's in there to make up the difference from the 5.6 millimeters that a laser diode normally takes up. So take a look at that. So on most laser diodes, you'll see that they're round, and they're most often gold plated copper. Whereas this is not cheap plastic with aluminum spacer. That's terrible. And the fact that there's no constant current driver on here is unforgivable. So, late 1990s, constant current driver. Brass with a retaining ring, so that way you could replace the laser diode. Copper housing, and this is pretty much the same. 2015, they added 2 lenses, which isn't a bad thing, actually. I'd say that's a positive. The aluminum housing right there. And yeah, so the biggest difference is the aluminum. And then garbage. Absolute garbage. So as you can see, when even talking about the modules themselves, there has been a significant change. And for the most part, I don't really necessarily disagree with them. Exchanging the copper for aluminum, not really that big of a deal. Even pressing in a laser diode instead of having a retaining ring, not that big of a deal. They're still both constant current drivers. This one, when it was bought new, like $50, and this one was like 10. So yeah, I'd say it's worth it. In fact, I'd almost say that this is the golden era of laser pointers right here. The 2010 to 2015 model. And I say this because even though aluminum is not as good as copper as far as heat dissipation, the fact that they have those double lenses in here, condensing the laser beam down, not only keeps dust from the laser diode, but also probably makes it a little bit more efficient. We'll test it out later on. And then this is an absolute mess. Let's open this up. Well, at least one thing stayed consistent, and that's the brass monolithic crystalline assembly holder. But other than that, yeah, practically everything has changed otherwise. And not for the better. Yeah, I figured real quick before we do some tests, I'd take that front aluminum spline section off, and sure enough, we can see that this also has those 2 lenses for condensing the beam down on the monolithic crystalline assembly. So, the only one that doesn't have the 2 lenses is actually the oldest one, which has the crystal assembly pressed up directly against the output of the diode. Interesting. Not expect the later ones to have lenses, but that is overall an improvement. Anyway, let's get to testing. So for my first round of testing, I want to figure out 2 things. I want to figure out the amount of optical power being generated by the laser module as far as what's coming out in 532 nanometers. And I also want to figure out what infrared leakage we have, which is why I have a little infrared filter here. For the rest of my test setup, I have my laser power meter, which is connected to my multimeter, which is set in volts DC, and there's a 1-to-1 correlation between how much power is being read by the laser power meter and how much voltage is displayed here. So 1 watt on the laser power meter equals 1 volt here. Very simple to figure out. I've got the laser module hooked up to my power supply, and I'm feeding in 3 volts. So we'll keep that the way it is, constant for all of the modules. So let's go ahead and figure out our tests. So turning on the power supply, and I'll be connecting the laser module up. So it starts off at about 30 milliwatts, goes down, center that a little bit better here. We'll let that settle. So it looks about 25 milliwatts. Only 5 times over the FDA limit. That's nice. We'll put this in front to see how much of that is infrared. So about 6 milliwatts of infrared. Okay. So I'm going to put a 20 on there because that's how much we get as far as green laser light coming out. Turn that off. Mark it. 20. Alright, and I'll do the same for the other two laser modules. Time to test 2015 power. (2015). Wow, that's taking a little bit of time to warm up. There we go. Not exactly as fast as 1990s, but we're getting there. So about 40 milliwatts. Only 8 times the amount of laser light as advertised. Let's see how much of that is infrared leakage. Oh, we did hit 40. Nice. Alright, and out of that 40, looks like 12 milliwatts of infrared laser light. So, yeah. Let's mark that down. 28 and 12. Boy, this is interesting to write on. You know what? We'll write down here. And 12. So, a little bit more infrared leakage, a little bit more power. That's either going to be more efficient or less efficient. We're going to figure that out. Alright, and now to test the early 2020s module. Why do I have the feeling this is going to be better or worse? Power. Oh, about 44 milliwatts. That's only about 9 times more than the label says. I will call that 45. How much of that is IR? So about 5 milliwatts. Yeah, about 5 milliwatts. Exactly. Well, 5 milliwatts of IR isn't exactly the worst thing. The green will get you before the IR does, but still, not that safe. 48. Are you gonna get 50? All right, you know what? We'll call it 42. And 5. Now that I've taken a measurement and checked how much 532 nanometer laser light is being generated by each module, which varies from module to module, so take this all with a grain of salt, we need to see exactly what our wattage into each module is. And of course, that's volts times current. I have my power supply set to 3 volts, and I've made adjustments for any kind of wire length and all that nonsense. So 3 volts is our voltage, and we need to figure out what our current is. So I have my multimeter set in current DC range, and all I need to do is connect the modules and see what we get. So starting with the late 1990s module, so let's hook that up. Like that, and then positive. Turn it on. .36. Go ahead, write that down. Okay. Moving on to 2015. What do we get? .40 or 0.4. That would explain why we're getting more IR out of there. We're giving the pump diode a little bit more juice. 0.4. Okay. And last but not least, the one that lacks a proper laser driver. Feels so wrong. Let's see what our current is. 0.2. Okay. Let's put 0.42. Well, that'd be some simple math. Let's do one last test, and that's to see how much 808 nanometer laser light is generated by the pump laser diode. Once again, I have my laser power meter here, my multimeter set in volts DC. Correlation was 1 to 1. So let's go ahead and grab the laser module from 2022. And what I'm going to do is I'm going to remove the monolithic crystalline assembly. So just grab that front section, pull it off. That. And connect my power supply. I'll turn it on. So this one actually had a pretty decent monolithic crystalline assembly. I might use it in another thing. Who knows? Go ahead. Turn on the laser. I'm blocking the number. So about 400 milliwatts. 388 milliwatts. That's a bit of power. Go ahead and test 2015. I'm betting that this is going to be about the same. They should all be about the same, given that the current is roughly the same. My guess is it's going to be a little lower. Oh, the glue is on this one pretty good. Ooh, already a significant difference in the quality of glue. However, that monolithic crystalline assembly wasn't so quick to warm up, so I might put the crystalline from the 2022 one. That might work better. Let's see what this is. So at 360 milliamps, sorry, milliwatts. Yep, 356. And I'm betting that the one from 1999 is actually going to be the lowest. Also going to be the most careful because unlike the other two, it's an exposed laser diode. Once the MCA is removed, we can take a look at the difference of that real quick once I pop it off. Alright. Yeah, pretty easy. Put it down. See how much laser light is generated. $377 milliwatts. About. Well, at least the pump laser diode is good. So let me point out the difference between having lenses and not. Where is that other module? There we go. Okay, so if we take a look at the one from 1995, we can see that it's a bare laser diode. So open can. You can see the crystal right in the center. This is a laser diode, kind of purpley crystal. And on this one, take a look inside there, you'll see that there's a lens, usually two lenses, and that's very similar to the one from 2015. So, but you can kind of see underneath there that there is another open can laser diode underneath those lenses. Can't really see much under that one. That's okay. We'll be taking this one apart, seeing how that flat pack laser diode looks. Try to carefully extract it without ruining everything. I already posted up a video on taking apart these style completely. I'll go ahead and link that down in the description. So we're not going to take this one apart, but let's see what that flat pack looks like. I'm curious to see. You know, I'm almost betting that squeezing around this with the vise might loosen up that that laser diode, that wedge in there. Be able to pull it out or not. That's a tricky one. That is a real tricky one. Can I pry it out? Something to pry with. Nope, I don't think so. Alright, so I'm going to give it a little squeezy squeezy. See if that does it. That worked. Okay, so let's take a look at the actual laser diode construction. See what we have here. So that's the laser diode emitter right there. Little purple crystal right there. See if we can remove this canister that goes around that very carefully. But the same kind of package they use in some CD/DVD burner laser diodes. So that's all you get. Not like a regular laser diode at all. See if I have a laser diode to quickly compare. Alright, I found a 5.6mm laser diode of which to compare the flat pack against. So, on the left is the flat pack. Has that metal slab, the laser diode mounted there in the front, with some grayish plastic that holds the wires in place. Take a look at the bottom there. That plastic versus a 5.6mm laser diode right here. I took the can off so you could see what's inside the laser diode package. The laser diode is not that black square, that's actually a photodetector. The laser diode itself sits at the very edge on that golden pillar right there. In fact, if you take a look at these two, laser diode is actually about the same size itself. So, but there's a big difference in quality just on the laser diodes themselves. This cheaper flat pack versus a full 5.6mm package like this. This doesn't even have gold on it. This has gold. Gotta pay for something. But yeah, big difference in quality. And of course, this does not get the heat out as well as the 5.6mm. So yeah, they pass the cost savings on to the customer. I've taken apart 3 laser pointers, done some tests, and have a rough timeline of the different versions of the laser pointers over the last 30 or so years. So I'll go ahead and throw that information on screen during this portion of the video. For now, I just kind of want to have some fun. So I am going to take the module from 2015 and I'm going to place on it the best monolithic crystalline assembly and get that all lined up and glued on. And I have something hopefully really special in store for the module from 1995, so you'll have something to hopefully look forward to. It is very simple. All I'm going to do is just put epoxy around that top, and I'm going to set the MCA on top and see if I can find the best portion on the crystal. I'm going to start off with my power supply lower, so around the 2-volt range, and work my way up, so that way I don't also burn the glue that holds the crystal into place. So a little bit of a dance, but overall it's a pretty easy task. Let's get at it. Connect the laser diode, laser module up, turn it on, lower the voltage. Alright, and find a MCA to put on it. I am going to use the MCA from the 2022 laser. I think that one operates the best. So I'm gonna just carefully kind of put this on there, see where the laser light kind of comes through, and see if we can find the hot portion of the crystal. Alright. Turn off the shaft light. And turn up the power a little bit. A little bit more. Alright, there we go. I just want to have it set to the point where it just starts blazing. That'll work. It's definitely making some green. Alright, so time to mix up some epoxy. That'll do. Now the hard part is not setting the MCA in the epoxy. Alright, I am going to move that off to the side now. We'll let that set a little bit. And I'll make my final adjustments when the epoxy is in the gel state. Alright, I'm going to set up and get ready for the one from 1995. Personally, I think that the laser pointer from 1995 has been an absolute trooper for lasting 30 years and still working. So I'm going to go ahead and do something special and turn that into a 593 nanometer golden laser pointer. To do this, I'm going to do an MCA swap. So I've already moved the one for 532 nanometers, and I have another one from a broken laser module sent to me by Barnett Unlimited. It is a self-frequency doubling laser crystal, and it looks about the same. So I'll talk more about the self-frequency doubling lasers in a video, but that's what we need. So let's go ahead and try and make this happen. Now, to my knowledge, the 593 nanometer lasers use 808 nanometer laser light for pumping. We got 808 nanometer laser light here, so it should be a simple swap. Let's see if this is possible. Of course, we need an MCA. Go ahead, break that off. And the reason why this one failed is because it had a bad pump laser diode. Pump laser diode failed. Please don't break the crystal. Oh, that's on there. Right, delicate parts. Clunky tools. I've seen better meetings. And we got it. So let's take a look at that versus the MCAs for the 532 nanometer lasers. We should see a difference right away. Zoom in. Overall, pretty close. Clean up some of the glue around there and we'll mount it. Go ahead, carefully set that on. And I'm going to turn on the power supply. Connect the module up to power first. What do you know? That helps. Alright. Wish me luck. Turn off the light. Turn on the light. Still need to see what I'm doing. Slide that by the crystal. Not getting any yellow yet. Turn out the power. No yellow action. And we have yellow. Wonderful. So, you can see some of that. My finger there. Oh, now you've seen it. You've seen a green laser pointer get converted over to golden. Nice. Very nice. Very nice. Epoxy time. Alright, I'm going to find the best spot for that. Zoom out. Carefully do this. Big capital, carefully. 72-point font. Oh, beautiful. Absolutely beautiful. Wait, where'd the beautiful light go? That looks pretty good, actually. Can we get better? We can. That's not bad. Oh, that's great. That's absolutely great. Check this out. Flying camera action away. Look at all the yellow amber we're getting. Nice. We'll go ahead and clean up that that laser pointer housing. Make that look fancy and it'll look great. What a great way to resurrect a 30-year-old laser pointer. Nice. This made the video worth watching, didn't it? So here's the fully modified module that was from the late 1990s and used to do 532 nanometers of green laser light. Now it's converted over to do 593 nanometers, which is a goldenrod yellow color. I took the brass tube assembly and collimating lens off the yellow module that was bad as well. Put that on. Turned out real nice. So at this point, it's good to go into a laser pointer. So let's break out the solvents, supplies, and start a montage. I'm building a golden laser pointer. Hold up, stop the presses. So, I've got some news for you. Anyway, I was getting ready to put together the laser pointer, and I needed to make an adapter because the module itself is about 12 millimeters and the inside of the hole is 13 millimeters. So I figured I'll use that piece of copper that came off the laser pointer from the late 1990s. So here it is. So I've got news for you. It was Earth all along. Look at that. It's brass. It's a copper plated brass part. That's hilarious. Yeah, I'd say that's the best green laser pointer mod you've seen so far. Time to set the focus on the front, make sure that that's as best as it can be. Put the end cap on, and it's done. And now for some final thoughts. Let's face it, we could all be a little irked that the quality of the 532 nanometer lasers has gone down so much over the years. But the other side of the coin is that something that cost $50 now costs about two and a half. That's the price of a candy bar. And it's astonishing that we can build these lasers so cheap now. If you want a quality laser pointer that's eye safe and you're just getting into lasers, I recommend that you check out Laserland Lasers. I have a review about the 510 nanometer grass green laser, and it's a good quality build, excellent for a beginner laserist. A little bit on where the quality is going to go perhaps in the next couple of years, and this comes from a 405 nanometer laser. So this is the outside casing of that laser. It looks about the same I removed the threaded section here in the front of the battery compartment because that's one change. So we can take a look at this part. It's actually two pieces. This top part right here, that is silver, is actually plastic, and it has a brass insert with the threaded section. So less brass, another point of failure. That's nice. Let's see. They also went and removed the brass ring on the inside here, and they just went and threaded the aluminum directly. Now, I think that these threads and aluminum don't hold up as well, but overall, that's not really a bad cost-saving measure right there. I can't really disagree. But here's the worst. Let's take a look at the module. Now, instead of aluminum or another metal here, we have plastic. That's absolutely terrible. That's not going to get like any heat out of the laser diode. And we got a 3.8 millimeter laser diode with a spacer that adapts it to the 5.6 millimeter hole there. Yeah, more plastic. I fear that that is the future of these laser pointers. Well, that's it for this video pretty much. I've covered everything that I want to, and it's been interesting to check out the differences. By the way, this is what that laser pointer that was from the late 1990s now looks like. Fully finished. Oh, you're gonna warm up now, aren't you? Look, it's still green, everybody. There you go. not quite fully 593 nanometers, but it's that most of the time, which is good enough for me. Absolutely beautiful looking laser pointer though. Well, I hope you enjoyed the video, and as always, stay tuned for more. And when I say more, I mean a lot more.